For some reason the computer just shut down my camera and I don't know why. So I'm sorry about that. We'll start back up. So I think I was saying angle N to 36 to angle A, angle G to the 36 to the angle A. So that would be a yes, and your reason would be angle side angle. Okay, which is very similar to the other ones. So there's different things you could do here. You could probably get an angle side if you wanted to and that kind of stuff. Just, of course, like always, you should avoid side angle because that's not a good congruency. So I feel like that one, there's lots of ways you could do if you were interested. All right, so number 2 says, what's wrong with this picture? Okay, and it looks something like this. I've told you before in class that I actually really like questions like this that are, you have to look at the picture and say, what's going on out here? Okay, so here we go. I've got little angle A, little angle B, 120 degrees on the inside, and I've got 110 degrees out here. So what's wrong with this picture? Well, the first thing that I see that's wrong with this picture is the fact that if this exterior angle here is 110 degrees, then B would have to be 70 degrees because these have to add up. They're a straight line pair, right? So they have to add up to 180 degrees. Okay, so that would make B have to be 70 degrees. And whenever I look at it like that, I've got 120 inside the triangle already. I've now got a 70 degree guy inside the triangle. And when I look at it, that's 120 plus 70, that's 190 degrees already. And I haven't even talked about angle A yet. So you could say something like the interior angles of the triangle would have to add up to more than 180. And that's before we even get a measurement for angle A, right? So I know that there's a problem there. The other stuff you could talk about, if you remember all of the little conjectures that we've worked on this semester, you might want to mention something like, well, I know that the exterior angle for a triangle is 110 degrees here, and that should be the sum of the other two angles. Should be 120 degrees plus A, basically, right? Because the opposite angles in here, when I add those together to make 180 degrees, the sum of these two angles should be the same as the exterior angle. That's a conjecture that we have already this semester. However, that's 120 plus A, and I only get 110 degrees. So it's basically the same fact that we have over here, but stated in a different way because now we're using that exterior angle conjecture. So got to be aware of that. Okay. So depends on how you see it. You might even see something else that I'm not looking at, but those would be the main two things that are wrong with this picture. Pick one. You don't have to give me both. Just pick one of the things that's wrong with it and tell me, and make sure that I can see what you're trying to tell me, either by labeling or making comments on your paper. Okay, given the following figure, if Cn is congruent to Wn and angle C is congruent to angle W, what we want to know is Rn congruent to On? That's the question. And of course, there's the why or why not statement. Okay, so always be aware that that's out there. Here's the picture. It kind of looks a bit like a crown. It's a scaling triangle this direction, ROW, and it's overlapping with a scaling triangle the other direction. Oops, sorry. You get the picture. CN. Oh, COR, and the intersection there is N. So, sorry about that. Not an artist, not an artist, not an artist. So we know that CN is congruent to WN. I'm going to put congruency signs there. We know that angle C, which is this large angle up here, is congruent to angle W, that large angle up there. I'm going to put 1 hash mark on those guys. So they want to know whether or not Rn, which is this little piece here, is congruent to ON, which is this little piece here. It doesn't look like it in my picture, but hopefully we'll see whether or not it is. So it comes down to, can I do something with this and make it be? Okay. So there's actually like these larger scaling triangles here that I'm dealing with. There's these smaller inside triangles, and then there's this little bitty triangle here on the edge. One thing that I will say is for sure we know this RO is congruent to itself because I see that in both the triangle CRO and WOR. So I'm going to put 3 hash marks on him just to make sure we know that he's congruent to himself. And so right now I feel like I've got an unusual, if I'm looking at this big guy. Oh, we can't even use that big triangle actually because he is, so whenever I look at this piece, it was NW, right? That was congruent to CN. So it's just this portion of this side, so it's not that larger scaling triangle at all that they're giving me the piece for. So I need to look at that, and so I'm assuming we're looking at this smaller triangle that's right here with this smaller triangle right here, and that's what I'm trying to put together and see whether or not they're congruent. So let's see what we got. When I look at this, I do still see, though, that this segment right here is intersecting this segment right here at N. And so to me, that gives me vertical angles right here at the intersection point. So I'm going to put 1 here. I'm going to give him 2 hash marks, and 1 here. Give him 2 hash marks. So what I just saw, what I'm telling you, is that I think angle CNR is congruent to angle WNO. Okay, and the reason for that, if I'm giving a reason, is because of vertical angles, right? Okay, so I see that those are congruent that way. I know that I've got this angle up here, this side here, and this angle here. So angle, side, angle. So these 2 triangles are congruent. Let's start with that. Triangle CNR is congruent to triangle WNO. Okay, those are the ones that I was just using. And that's an angle side angle because of angle side angle. And if you want to, you can call it the angle side angle congruency conjecture. Okay, so I know that those are congruent, but that wasn't the question. The question was about RN and ON. So those are these little pieces right here. However, now that I have this triangle is congruent to this triangle, I'm going to say, therefore, the 3 little dots, right? Therefore, RN is congruent to ON. We know it is. And the reason for that one is because now I have congruent triangles, so I can say corresponding parts of congruent triangles are congruent, right? By CPCTC. Okay, and if you're not sure about that guy, go back and look in your notes. Corresponding parts of congruent triangles. And remember that this can be any polygon in there are congruent. Okay, that's a lovely little conjecture. We use it all the time. So CPCTC. Use him and love him. He's not going anywhere. Okay, so that's number 3. All right, moving on. Number 4. Number 4 is another what's wrong with this picture. Oops, sorry about that. Okay, the picture looks, oh goodness, I'm sorry in advance, guys. I don't have a ruler with me. So the picture looks kind of like, it's got these extended exterior angles on it. I'm going to do something like this, something like this, and of course Take something like this. All right, sorry about that. Of course, I didn't give you any labels on them, so we don't have any letters to talk about. I know that this upper left-hand angle in there, it's a what? 1, 2, 3, 4, 5. It's a pentagon. This upper left-hand interior guy is 135. We have these congruency markings on these two exterior angles. We know that this one right here is 49 degrees. And we know that this exterior angle up here at the top right is 154 degrees. Okay, and of course I didn't bring my calculator with me, so that's going to stink. And I don't have students in front of me to do the math for me. Stinker. Okay, so first thing we need to know is about the exterior angles of this pentagon. We know that all exterior angles, remember we talked about this, if I were to shorten the length of these sides and push all these angles together until all of them were intersecting at the same vertex right here, then the exterior angles would make a complete circle around that point, right? So what we need to know is exterior angles of a polygon, and again, that doesn't matter which polygon, any polygon, add up to 360 degrees. It's a circle, right? Okay, so that's the conjecture or the property or whatever you want to say that we're going to be using, and that's the sum of the exterior angles is 360 degrees. And we just know that, we've talked about it. So I've got 360 degrees total. I've got 154 degrees that I'm going to take out, so check my arithmetic as I go. 206, I believe, is what I have left in there. Okay, I'm going to take out this 49 degree guy. Stinker. All right, so I have to actually do it old school. So I've got 157 degrees. I need to do a tiny bit of arithmetic up here on the left-hand upper corner because I know that this makes a straight line pair. So that'll be 180 degrees minus the 135 degrees. So the exterior angle there is 45 degrees. Check my arithmetic, make sure everybody agrees. Okay, so I've got 5 exterior angles. I've got 3 of them I have numbers for, so I'm going to pull that 45 degrees out. I think that's 112. Okay, so if there's a difference in my arithmetic, please check me. Yeah, I think that is true. Okay. What's wrong with this picture is what we're after. Oh man, well let's see. Okay, so let's keep going. So as I do this, I also need to do some interior angle stuff for me to figure out what's going on. So we'll talk about that in a second. I've got 154, sorry. Yeah. So let me go ahead and get this number right here. If we do this, it's 112, and I divide that by 2, then I'm going to get, what is that? 56 degrees. Is that right? Both of these should be 56 degrees. Okay. So if that's true, then let's see what we've got going on the inside, because I think that we're going to see a different measurement whenever I do the inside of this guy. So that's what I think these should be. All right, so these were exterior. Let's talk about interior. Well, the interior angles of this particular pentagon, we know the formula for interior angles is 180 degrees times n, which in this case is a 5-sided guy, minus 2. So 180 times 3 should be, not degrees, should be 540 degrees. If I've done everything correctly in my head, I'm pretty sure I have. So let's go ahead and figure out what all of these angles are. So as I do that, I've got a 135 degree guy. So all of my interior angles should be adding up 135 degrees. We need to do a little more arithmetic. So what's the inside guy there? 180 degrees minus 49 degrees. This is not the day for me to forget my calculator. So the inside guy should be 131 degrees, if I've done that right. Double check the arithmetic. Yep. Okay, inside of this guy, 180 degrees minus 154 degrees, 26 degrees on this inside guy. I've already got that 135 guy in there. So then these are the same angle. I just need to know what 180 degrees minus 56 is, because those will be both the same measurement, right? So for 124 degrees on each of these on the inside. So there's two of those. I need 124 times 120, or times 2, so that's 8 for 248, right? If I did it correctly, please double check my arithmetic always. So I need to add these all up. We know they should add up to 540 degrees. So let's double check. 6 and 8 is 14, 15, 20. Carry the 2. 3, 6, 8, 10, 14. Carry the 1. 2, 3, 4, 5. 540 degrees. Oops, I've got a problem. So I'm getting the right answer, and I'm not supposed to, so... let's see what the thing says. The exterior angle of 35-degree angle is 45. I've got that. 3 exterior angles are 49 degrees. I don't have 49 degrees. Why do I have 49 degrees? Why do I have 56 instead of 49? Oh man, if only I had somebody here to do all this arithmetic for me. Sorry guys. So I've got a supposed exterior angles of, according to my key, 154, 147, 154. The 147 is 49 plus 49 plus 49. I've only got one of those in there. And the 45. So this in here should be where my mistake is, if I made a mistake. So let's double check my arithmetic there. Because the key said whenever we add these all up, we get 345 or 46 degrees instead of 360 degrees. So somewhere I've got something wrong in my arithmetic. So I definitely have the 45. That guy's okay. I've got the 154. Let's just add them instead of subtracting. That might help me. 154 plus 45 plus 49. Okay, so the problem becomes, why are these guys 49 degrees instead of 56 degrees? Let's see what we got. 9 and 9 is 18. 5, 10, 14, 148. Oh. Sorry. 248. 5, 10, 14, 248. And I'm supposed to be subtracting that from 360 degrees. 2. It looks like 112. What is wrong with my arithmetic, guys? Why aren't y'all here to help me? Because in my key it says 2 of those guys are 49 degrees. What's wrong with this picture? Oh, stinker. It's something that was forced. So they should be 56 degrees. This would give me 56 degrees. So So all of my calculations are correct. Yay. The problem is I wasn't paying enough attention to this notation right here. This says it's 49 degrees, and look, there's the congruency guy. So I just had these guys marked as congruent, and I was saying, oh, they're the same measurement, but no, it actually says, if I look at the picture very closely, this one, and this one all have the same 1 hash mark congruency. So even though the measurement should be 56, maybe that's what's wrong with it, the measurement should be 56 degrees, but according to our picture, they're marked as 49 degrees. That's why I'm having a problem. So what's wrong with this picture? What's wrong with this picture? What's wrong is that two exterior angles should be 56 degrees, but the picture has them marked. I'm like, my math is coming out right. Why is it coming out right? The picture has them marked as 49 degrees. That's what's wrong with the picture. If only they had left it alone, then I would have the those two angles would be 56 degrees, and all the math that I had would be correct. But whenever they mark it as it has to be congruent to that 49 degree guy that's up there, this is congruent to this, is congruent to this, then I can't make it be 56, which is what I should have done, should be able to do, but it's not letting me. So they're forcing me into a 49 degrees, and that is incorrect. Okay, so perhaps those two guys right there should have 2 hash marks on them so that we can say they're congruent to each other, but they're not congruent to the 49 degree guy. That's what's wrong with that guy. Yay. All right, cool beans. Whew, I was starting to think my arithmetic was wrong, which could happen. Okay, this one says true or false. If true, give a reason why. If false, give a counterexample. Okay, you can find the measure of each interior angle of an equilateral n-gon by using 180 degrees times n minus 2 divided by n. Okay, so let's read it again. So what it's saying is this formula tells me the measure of an interior angle in an equiangular n-gon. Okay, so for our purposes, that means equiangular means that it's regular, right? So we're talking about a regular polygon here. So what they're saying is, say that this was a triangle. The n-gon there, it would be a 3-sided polygon, right? If this was a triangle, then we know that all of the interior angles would be 3 minus 2, 1 times 180. So the interior angles of a triangle add up to 180 degrees, we know that. And if it's regular, I can divide by 3, and 180 divided by 3 gives me 60 degrees. So that's the triangle. That's the measurement of each angle inside of a triangle that's equilateral. Okay? So what they're saying is this will work for any n-gon, okay? Any polygon. So this is true. Hopefully you see that. And the reason why, it says, if so, give a reason why. And what's happening is the top part is the formula for all interior angles of an n-gon. And the bottom tells me divides that total sum into n equal parts. Okay, and that's what it means to be equiangular, right? They all have to be the same, so therefore if I want 4 angles. There's 360 degrees. I want them all to be the same. I would take 360 degrees, divide by 4, because then I'd be dealing with a quadrilateral. And 360 divided by 4 would be 90 degrees, and that would give me each equal angular angle measure for a square, which is true, right? All of those are 90 degrees. So we could do that for any n-gon. All right, I like it. That one's true. Good deal. Okay, that's number 5. Moving on, number 6. Prove the following. The diagonal connecting the vertex angles of a kite is the perpendicular bisector of the other diagonal. So it's a proof, guys. You can do it using any of the methods that we've used. They need to be a formal proof method. So I think at this point, you know that those are flowchart or paragraph proof or 2-column proof. And I think that most people are probably going to be like, oh, I'm going to use a 2-column. But if you don't want to use a 2-column, that's okay. Okay, so whichever you're going to do. So first off, we need a kite. Okay, I'm going to use the picture that I have on the test solutions part. I'm calling it A, B, C, D. I did turn it sideways, sorry. So here's this. Oops, those are terrible diagonals. Sorry. Okay, so we're given kite A, B, C, D. And what we want to prove or show is that, what did it say? I'm sorry, let me read it again. Show that, where is it? The diagonal connecting the vertex angles, that's the A to the C. So show that AC, that's your diagonal, is the perpendicular bisector of the other diagonal. Is a perpendicular bisector for DB, which is the other diagonal. So what they want me to show is let me put in here a middle point, an intersection point. I don't think that in my picture I have one of those. I called him M. That's what I was about to call him anyway. So M. So we're going to show DM is congruent to MB. That's what we're about to show. All right. Okay, so I kind of used a paragraphy proof type thing on your solutions manual, or in your solutions. I'm going to go ahead and give a 2-column proof here, just like we normally do. So we've got a statement over here, and over here we've got a reason. Okay. And we're going to start out with the fact that these guys are kites and work from there. So, or that this guy, ABCD, is a kite. So the definition of a kite is that the 2 adjacent sides are congruent. So I know AD is congruent to AB, and I should probably start with kite ABCD, sorry. And that would be my given. So stick that guy up in there, sorry. But AD is congruent to AB, and CB is congruent to CD. And the reason we know that is from the definition of a kite. Okay, so I'm going to put 2 hash marks on these guys. All right. So I know those are. I also know that, well, let me take a step back here. This whole entire diagonal AC is congruent to itself. We'll call it CA, right? I know that because it's the same segment. Okay. So now if I look at that way, if I put a 3 hash mark on that diagonal down the middle, then what I know is that triangle, and let's be careful about this, we'll call it ADC. A, we'll say the short side, D and C. is congruent to triangle A, the short side, ABC. Okay. And the reason I know that is because I've got side, 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 and side, side, side. So side, 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 triangle, conjecture. Oops, congruency conjecture. Okay, so we know that one for sure. Okay, because of that, and in your notes it says the reflexive property, but that's the same segment, it means the same thing. Because of that, I know that all the little parts and pieces inside of that triangle are congruent to each other. So I know that this angle up here, because it's part of ADC, this angle up here is congruent to this angle here. So let's get that in there. Angle DAC is congruent to angle, and I did BAC because they're corresponding parts of that congruent triangle, so CPCTC. Okay, so now I'm looking at it and I'm going, oh, I've got this big triangle here and this big triangle here. I'm trying to prove that this diagonal was a perpendicular bisector to this diagonal. So I need these little pieces here to be congruent, and I need these angles to be 90 degrees. That's what I'm up for. So that's where I'm headed with this guy, if I can get that far. For our purposes, I now am looking at these tiny triangles right here. Okay, and I've got side angle and side angle, and whenever I look inside of those tiny triangles there at the top, I see, oh look, they have this side in common for these little triangles. So what I'm looking at here is I see that AM is congruent to MA. Again, they have it in common right here on the small triangle. So again, that's same segment, right? And what that does for me is it gives me side, angle, side. I can talk about just that little bitty piece there. Okay, so I've got triangle ADM is congruent to triangle ABM, and that's because of side, angle, side. Okay, so because I have these two small triangles congruent to each other, now I know all of their corresponding parts are congruent, right? So I know that, for instance, DM is congruent to BM because it's a CPCTC situation. I also know that angle, I'm going to say it together using the same reason, angle DMA is congruent to angle BMA, also because of sides or corresponding parts of congruent triangles. Sorry about that. There we go. Okay, so these guys are congruent. I need one more little piece. So I've got this piece is congruent to this piece. I've got that. So I know it's a bisector. I just need to know that they're perpendicular. Now what I've got here is that the small angles in there are congruent to each other, and I need to talk about the fact that they're 90 degrees. So whenever I look at that, I see that angle DMB, now that's this straight line angle through here, right? It's a straight line, DMB. Is 180 degrees. That's the definition of a line. Okay, and I see that these two are congruent to each other, and they together combine together to give me 180 degrees. So that's the angle sum conjecture. DMA plus, let's say the measure, plus measure of angle BMA equals 180 degrees. Okay, that's the angle sum conjecture. All right, we're almost there. Now, because these two add together to give me 180, And because those two are also congruent, we know that, then I can do a substitution step basically. So I can say, let's substitute out, for instance, instead of BMA, let me substitute in DMA. So I've got measure of angle DMA plus the measure of angle DMA equals 180 degrees. That's the substitution. So all I did was sub it out. And now look at that. So 2 measures of angle DMA equals 180 degrees. Okay, that's just adding together combined like terms, however you want to think about that. I'll call it combined like terms because we're getting into some algebraic stuff now. And then I'll use divide both sides by 2. The measure of angle DMA equals 90 degrees. Okay, if that one is that way, that's from the division property of equalities. That's what I used. I divided both sides of the equation by 2. All right. And now, oh my goodness, we're almost done. I used the whole piece of paper. Because I know measure of angle DMA is 90, and because I know that it's congruent to angle BMA, I know that the measure of angle BMA is also 90 degrees, and that is definition of congruency. All right. So, now we have both of these angles are 90 degrees. Yay, we proved that. We've got a perpendicular bisector going in there. We see that these two pieces are congruent to each other. I'm out of space, but I would add a therefore statement. Let me pick up another piece of paper. Therefore, AC is a perpendicular bisector for DB. And I'm going to throw in a quite eloquently done there because, oh my goodness, that took me a whole sheet of paper. There we got it. All right. So lots of stuff going on in there. Hopefully you can follow the gist of the proof and the reasoning behind it. If you have any questions on it, let me know. We'll work through it. All right, moving on. Yay. Number 7 says, oops. Got multiple pages here. True or false? Yay, true or false? The opposite angles of a parallelogram are congruent. Give an example or a counterexample. So you just need to give me some kind of parallelogram. Remember that in most cases like this, we want to make it more generic, so try to not make it look like it's a rhombus or something like that. Don't make a rectangle, anything like that. In the picture that I gave you here, I've got angle 1, 2, 3, 4. I usually number things like this. 5, 6, 7, 8. Okay, these are parallel, so going this direction, I'm going to give them 2 chevrons. Going this direction, I'm going to give 1 chevron. And we're after, what were we after? True or false? Opposite angles of a parallelogram are congruent. You don't have to prove it, you just have to give me like an example and show me how you know that. So we're trying to say true or false, angle 3 is congruent to angle 6. That's what we're after. Okay. So we got some stuff we could do here. It all comes back to basically week 1 of our class where we talked a lot about parallel lines, right? So I want you to use those parallel line postulates and all that kind of stuff that we have here. I'm looking at this line going across the top and this line going across the bottom. Those are parallel. And this line, let's call this line 1, line 2, line 3 going down here, and line 4 going down here. So line 4 here is a transversal between these two parallel lines, line 1 and line 2. So whenever I look at that, I'm going to skip for a second. I'm going to do 3 is congruent to 8. Okay, hopefully everybody's okay with that. And the reason why is because angle 3 is congruent to angle 8 because of alternate interior angles. Does everybody agree? If I ignore this piece over here, just look at these parallel lines. This guy's cutting through it. Those are alternate interior. Okay, and then what we want to know is 6 congruent to 8 when I use the parallel lines 3 and 4 here. And now we're talking about the transversal being line 2. So if you needed to, you could even pick your piece of paper up and rotate it around, right? We're talking about this line's parallel to this line and looking at line 2 as my transversal. Okay, so if rotating your paper helps you, then rotate your paper. It's fine. Okay, so if I look at that, I see 8 is in the same position as 6. It's both of those are above line 2 here, and both of those are to the right, in this case, of the parallel lines. So yeah, I think angle 8 is congruent to angle 6. And because they're in the same position there, that's called corresponding angles. Does everybody see that? So to me, this picture is enough right here. I've got 3 to 8, 8 to 6. I can see that those are all congruent. So yes, 3 is congruent to angle 6. So therefore, it's a true. And this would be a great picture for you to use to show me that. Okay, and that's plenty. I didn't ask for a proof. However, on the test, I could ask for a proof on this one, and that would be something I would expect you to be able to do this one. That's actually a fairly simple, for lack of a better word, proof, because I just did 3 to 8, 8 to 6, and then you would do a transitive property there. 3 is congruent to 8, 8 is congruent to 6, so drop the 8 out, so 3 must be congruent to 6. So I think we could probably do something with that. Okay, number 8. Be sure you know all the properties of, oh, sorry, this is not number 8, this is just a little caveat I put there. Be sure you know all the properties of the various quadrilaterals, i.e. rhombus versus rectangle. So on that one, the quadrilaterals, go back and look at your definitions of quadrilaterals. I gave out a page so you can see the difference. So what are those? And also, just a word, you will have a word bank again for this test for the proofing. And so this first page is exactly what you had on test 1. Parallel lines, properties, generic properties of equalities, general stuff, postulates, triangles, and corresponding parts of congruent triangles down there at the bottom. Okay, but on the back is new. We didn't have this for the first test. So there are properties of quadrilaterals and all those lovely conjectures that we went through for kites and trapezoids and all that. So be sure that like you can look at what do you think the rhombus diagonals conjecture means, okay? Because you're not going to have a definition for these on the test. So rhombus diagonals conjecture. Well, it probably means what? Diagonals of a rhombus are congruent. Okay, that's probably what it means. So you can look at it and see what's going on there. Oh. Yeah. So making sure that I got them all. And for instance, rhombus angles conjecture is probably opposite angles in a rhombus are, now I'm wondering about my rhombus diagonals. Let me think about that. It might be, go back and look because it might be like they bisect each other. I think they bisect each other. I think that's part of a parallelogram diagonals. Any parallelogram, they should be bisecting each other. So I think that's what's going on there. Rhombus angles, opposite angles of rhombus are congruent, right? And then all these circle properties, circumference conjecture, arc length conjecture, all that stuff that we worked on, chords of central angles, you'll see that. But make sure you know what those different properties are so that you can apply them. All right, number 8. Fill in the blank. If 2 chords in a circle are congruent, if 2 chords in a circle are congruent, then there are 2 blanks, are congruent. Okay, so think about it like this. Oops, it's a bad circle, but you get the point. If I have a chord here, and I have a chord here, and I know that this guy is congruent to this guy, let's call this A, B, C, D. If I know that the chord AB is congruent to the chord CD, then what do I know also? The arc AB is congruent to the arc CD, right? Oops, sorry. The arc AB is congruent to the arc CD. So if I have those chords, then I know that the intercepted arcs are congruent, right? Because they are defined, that portion of the circle that they're intersecting is defined by the chord right here. So you can definitely see that their arcs are congruent also. All right, getting there. Number 9. Number 9 says, prove inscribed angles that intercept the same arc are congruent. Inscribed angles intercepting the same arc are congruent. All right, so again, this is going to be another proof guy. You need to decide which way you're going to do it. Are you going to, use 2-column proofs or what? I'm just copying over the picture that's given. So it says ACB is an inscribed angle and ADB is an inscribed angle, and it gives this as circle S. I don't need to put the center there, but you get the point. Okay, so here's what it says. The inscribed angles intercepting the same arc, so AB is indeed intercepted by them both, are congruent. So I need to kind of figure that out is what we're after. Okay. Well, this is going to use one of those properties that we have about inscribed angles. So looking at your thing, inscribed angles intercepting arcs conjecture, that's it, and inscribed angles conjecture. So the first conjecture says, look, if I have, we might want to go back to central angles, right? So statement and reason. Let me talk you through it first, and then I'll give the proof. So if I have a central angle right here at the center, that's probably why I have S there, ASB would be the same measure as AB, right? So I know that. However, this is an inscribed angle, so it's got to be, what's that relationship from the inscribed angles conjecture? Half, right? So I know that, so let's start out with, we're given circle C, or circle S. With angle ACB and angle ADB intercepting arc AB. That's just given. So start there. Okay, what was I given? There we go. Okay, what we know is that the measure of angle ACB is equal to 1/2 the measure of arc AB. And I also know that the measure of angle ADB is 1/2 the measure of arc AB. Okay, and I know that because of, I just said it a second ago, inscribed angles conjecture. Okay, that's how I know it. So both of them are half of that measurement. Whatever that measurement is, I don't care. I just know they're both half. So now that I know that they're both half, wait a minute, I see they're equal to the same thing. I can set them all congruent to each other, right? Okay, so now I've got the measure of angle ACB, or equal to each other, is 1/2 the measure of arc AB, which is equal to the measure of angle ADB, right? Just setting them all congruent to one another. And then, so that you could call that substitution or whatever. This will give me the measure of angle ACB is equal to the measure of angle ADB. Oops, ADB. Because I'm going to drop the guy out of the middle and I'm going to be left with the guy on the left and the guy on the right. And that is the transitive property, right? That's what I'm after, transitive property. Now I have the measure of this guy is congruent to the or is equal to the measure of this guy. They actually want me to show that the angles are congruent, not that their measures are the same. However, we know angle ACB is congruent to angle ADB because that's the definition of congruency, right? Okay. So that's what they wanted me to show. I am done. Make yourself a little statement. Therefore, or you can use the three little dots. Therefore, inscribed angles intersecting the same arc are congruent. Done. Okay, and that guy is a way easier proof than the one we did a second ago with the kites. So no worries. Y'all should all be good. All right, and I'm coming up on an hour on this video. There is one question left, so hopefully that ends up pretty perfectly for us. Let's look at number 10 and see what it says. Give an explanation of what pi truly represents and one way you could demonstrate this to your students. All right, because you all want to be teachers at some point, the question is, what does pi really represent? And remember that we did a couple of little activities where you could play with those and see things. We did coffee filters. We talked about an activity you could use in class. So hopefully you know that pi is a ratio, circumference of a circle divided by circle, the diameter of the circle. So basically we're saying how many times, if I have this circle and I have this diameter, circle A we'll call it, how many times if I cut off this particular circumference all the way around, that's what we did with coffee filters, how many times will I be able to cut that into diameters? One of the things that we could do is we could take this diameter and we can make it into a string, that length, and we could say, hey, look, it goes once, twice, 3 times, and I have a little left over, right? Okay, so it's approximately 3.14. That's what we use as our decimal approximation. So the idea being that the circumference can be broken up into 3 and a little bit more diameters of the circumference. That's what it actually physically represents. That's what we're trying to do. What was the second half of that thing? One way you could demonstrate this to your students, that's it. So remember that we talked about, well, you could do the coffee filter thing just like we did in class, but we talked about you could do different objects, right? And have them measure it like a coffee can, a bottle of water, a butter dish. The book mentioned wheels or tires or whatever. So lots of objects, bring them in, have the students measure the circumference, have the students measure the diameter, and then have them come up with that ratio C over D. And hopefully it comes out pretty close to 3.14. If it doesn't, if some of their stuff is, say, 3.2 and some of their stuff is like 2.9, remember we talked about you could take all of their measures and average. And a lot of times that comes out nicely, especially if you have a large group of students and you get a lot of measurements from the different ones. That'll come out pretty good. So that works out. Okay, one last statement on your review says, recall that these are only sample questions. Anything we've done is fair game. Be sure you can do proofs, transformations, tessellations, and discuss geometric solids such as prisms, pyramids, etc. So it's just because I didn't have time and space and whatever to talk to you about the other stuff. So go back in your notes, make sure that you talk about the different transformations, you understand those. These are solid state transformations or rigid state transformations, depends on what book you're looking at. They are translations, which means slide. Remember the SL with the SL. Rotations, which means turn. Remember the T with the T, the hard T here, before you get to the Asians, right? And then reflections, which means flip. And again, you got the FL with the FL there. Okay, so we had those solid state transformations. We did a lot of those. We talked about what that means for tessellations. I would not put it past Dr. Webster to give you a shape and tell you that you need to use that shape to create a tessellation. So make sure that you can do stuff like that, okay? And then the pyramids and the prisms and the solid stuff, make sure that you've seen that. Make sure you know what they mean. I just don't have enough time to go into it all. We're over an hour now, so I hope that helps you. I'm sorry I'm out of town. I hope you do well on the test, and I'll see you next week. All right, thanks. Bye-bye.